Hi everyone, today I'm going to show you Qnect, a REST framework that takes you from a simple quantum circuit all the way to a global quantum network. So let's build something awesome together. Let's start simple. First we can create a bell pair, the hello world of quantum computing. This single line creates a quantum system with 2 qubits. That's it, no configuration files, no boilerplate. Now we create entanglement. First we put qubit 0 into superposition with a Hadamard gate. Then we entangle it with qubit 1 using a CNOT gate. These 2 qubits are now quantastically entangled. So let's prove that the entanglement works. We'll create 10 bell pairs and measure them. Perfect. So it works. Now that we know that, we can go over to part 2. Now, here's where it gets exciting. We're creating a distributed quantum network. Each node will have its own independent quantum system. This models how real quantum network works if each location has its own quantum processor. We add Amsterdam as a node with 4 qubits. In a real quantum network, this would be a quantum computer in a lab in Amsterdam, where a lot of cool things are happening in the real world. Now we add Singapore, but watch this. We're using a different backend. The mock QNPU backend simulates what it would be like to connect to an actual quantum processor. It mimics the API calls you make to the real hardware, or at least what I think. And this is the cool thing, you can replace the backend type with real hardware later. Here's the magic. We're connecting Amsterdam and Singapore via a quantum satellite. 550 kilometers orbit is realistic. That's where quantum satellites like MeQs operate. And the 0.85 fidelity means 85% of our quantum states survive journey intact. Of course, this is just simulation. Watch the resource tracking. We start with 4 free qubits, and after creating the EPR pair, we should have 3. So this single line, if we see it here, creates quantum entanglement between 2 continents, simulating what will be possible with the quantum internet. Okay, let's run this and see what happens. All right, so we can see they are entangled here. This is crucial. We're checking that the entanglement is properly tracked in our non-local store. So the framework maintains the quantum correlations between these distributed qubits. Measure one, and the simulation ensures the other behaves according to quantum mechanics. So let's see what's really happening. So we could look a little bit under the hood. We are in distributed mode, so each node has its own quantum system. This architecture matches, at least as good as I can, how real quantum networks are being built. Of course, with some likely modifications. So let's see how it works. And just to remember, each node has its own quantum system. EPR pairs. So EPR pairs has are tracked with non-local correlations. Classical communication channels established. Let's take a look at how this works. So here you can see the mode is distributed. We have a total of 2 nodes and total allocated qubits are 2 and total links are 1 and protocol operations recorded is 1. That's correct. And for the final part, let's look at how the feature where Qnect generates actual NetQASM code that can run on real quantum processing network hardware. While we are simulating the quantum operations, the generated code is at least supposed to be production ready, although it might have some flaws here and there, but let's see how this works. There we go. So just a quick example of how it can generate NetQASM based on your Qnect code. So what did we just do? We started with a simple qubit bell pair, then scaled up to simulating a global quantum network with nodes in different continents, connected by a satellite with different quantum backends, generating real executable code. And that's the power of Qnect, from local circuits to global networks, all with one simple API. I think the quantum internet is coming, and with Qnect, you can start building and testing for it today. Thank you.